Well, thank you all for being present here at this opening session. The CASS chapter in Rio Grande do Sul is very honored to present the first talk this morning or day of the 10th edition of the school. We'll have 11 talks in those 4 days, as already mentioned previously. And the first talk will be given by Massimo Alioto. Let me introduce Massimo, the speaker this morning. Massimo will speak about ultra-wide power adaptation for next generation always-on system. And Massimo is out in Singapore now, where he is a professor at the Electrical and Computer Engineering Department at National University of Singapore. He's the leader. Excuse me. He's the leader of the Green IC group, the Integrated and Embedded System area, and the FD Fabrics Industry Sponsor Lab on FD-SOI Intelligent Interconnected Systems. He has been previously associated with several institutions. He worked at the University of Siena, Intel Labs Circuit Research, University of Michigan Ann Arbor for a few years, and University of California, Berkeley, and EPFL. He is a very prolific author of 300 plus publications on journals and conferences. He has published 4 books, including the one that calls that's titled Enabling the Internet of Things for Integrated Circuits, Integrated Systems. As you all know, Massimo's primary research interests include ultra low power circuits and systems, self-powered integrated systems, near threshold circuits for green computing, and what we're going to be speaking today, widely energy scalable integrated systems, circuits for machine learning, intelligence, hardware security, and other applications. He is the current editor-chief of the IEEE Transactional VLSI Systems. He was a deputy editor and have several editorial board assignments. He served as a guest editor of several issues, and his technical program of many members. So it's our pleasure to have Massimo. Massimo is also an IEEE fellow, should add, and he will be speaking for this hour on this very exciting power adaptation issue for next generation always-on system. So the floor is yours now for the first talk of the workshop, dear Massimo, and please say hello and certainly our audience will appreciate very much what you have to share with us this day.
I guess you can hear me okay?
Yes, you're being heard.
Good. Well, first of all, thank you, Sergio, and thank you all. I'm very honored to be to introduce this talk, the first talk to this event, and I'm really amazed by the energy that is behind the organization of this event. In spite of this quite unique, quite peculiar situation worldwide, it's really encouraging to see that there's a lot of vibrancy and energy. And by the way, I would love to be in Brazil right now, but unfortunately, that's not an option. Now, let us move on and let us plan the next hour, the hour that we'll spend together. We're going to talk about one of our research areas that we are investigating, and this is about ultra-wide power adaptation to enable next generation always-on systems. So this presentation is structured as follows. First, we'll talk about the context and the motivation. So we'll share that actually things are a little more complicated than we usually tend to think. So adaptation is an essential property and requirement in always-on systems. Then we'll talk about how to scale up performance, reduce power down to the very minimum that complies with the very limited power budgets offered by energy harvesters, and then I will wrap up. So let's get started with energy autonomous integrated systems and what they really are. Well, essentially, we're talking about IoT nodes. So the nodes, the devices that are at the lower tier, and let me just actually enable the pen so that once in a while I'll be able to highlight things for you. We are focusing in this presentation on at the edge of the IoT. So sensor nodes with very limited power budget. And by the way, Sensor nodes were expected long time ago to be mostly dormant and being duty cycled, but these days, actually, you want them to be very responsive and always on or mostly on. And this poses a very fundamental challenge in terms of power consumption and its trade-off with performance, which is the core of this presentation. Now, everything is really constrained by the energy and power availability in IoT nodes as available from the source, the energy source, which is typically a hierarchy. You might have an energy harvester, a battery, and hopefully miniaturized, as well as a supercapacitor. And those are combined in proper ways to achieve the best of the two worlds. For example, the high energy density of energy harvesters and the high power density of supercapacitors and or batteries. Now, depending on what type of energy source we have, the average power certainly matters, and it is the main concern in battery-powered systems, because this essentially determines the lifetime of the system. So you will have a decay in the energy stored in the battery. Once it hits zero, the system stops working. And the slope is basically dictated by the average power of the system. Then you can have hybrid energy sources. So you're going to complement the battery with, let's say, an energy harvester, let's say a solar cell. And in that case, essentially, you are reducing the power, the amount of power being withdrawn by the system by the amount of power that is being provided by the energy harvester. And if the energy, the power of the energy harvester actually completely offsets the average power absorbed by the system, then you can actually aspire to nearly perpetual operation. So we're talking about decades of operation for typical integrated systems. Then you have a third and increasingly important category based on pure harvesting. So there is no energy storage. There is only harvesting. And this means that the peak power, whenever the peak power goes beyond the available instantaneous power from the harvester, the system gets shut down. So again, the lifetime will be limited, not in its extension, but in terms of intermittency. And then you have a new class, a recently proposed class of systems that is called battery indifferent, where you can operate off of a battery to continue operation at higher performance whenever the energy in the battery is available. Or if the battery is empty, is running out of energy, then the system can still operate continuously by tapping into the power availability from the energy harvester. Of course, at limited performance. But this allows to combine these two to extend the availability of the system in spite of the intermittently available energy in the battery. Now, we all know that classically, what we do to reduce the average power is to sleep most of the time and have once in a while some active task. And more duty cycle, more aggressive duty cycling, it means longer sleep for a given active mode, means lower average power. But actually, and this is actually pretty easy to achieve, but this comes at a price. The system will be mostly dormant, mostly unavailable. And the power can also be further reduced through voltage scaling. Now, in recent systems where it's actually, the main purpose is to detect events and then turn on data analytics, on-chip data analytics, whenever there is an event of interest, well, those have to be always on, and it means that their level of performance need to be very different depending on whether an event is occurring or not. For example, if you have a speech recognition system, if there is no speech, as we have here on the left, well, then you don't need to actually turn on the speech recognition system because there is no speech, and you have a speech detection system. When there is speech, then you turn on the big machine learning engine, and this will come at a power cost, but occasionally, and it will require a much higher level of performance. So this is really what the IoT is requiring more recently, which is you need to achieve low energy in the common case to make sure that the average power is low and complies with the lifetime target of the system. But at the same time, the maximum performance, although occasionally it matters as well, because sufficient performance has to be delivered whenever there is an event of interest. So, and in this case, you want to scale up the voltage and even boost up the performance in any possible way, which is what we are going to discuss in the next few slides. By the way, there is another concern that we need to take care of. So, for example, in battery indifferent systems or in purely harvested systems, the power of the system need to comply with the power availability from the harvester, and this is instantaneous. So if, let's say, you have a solar cell that is actually providing very little power because the lighting conditions are being not very favorable. Let's say you are indoor and it's, let's say, twilight. Well, in that case, you have little power, and the system has to reduce this power down to what is called minimum power. So in this case, it's not about energy, it's about power. Okay? Now let us try to make sense of what type of power we are talking about. Well, if you look at practical harvesters, they typically, and I'm referring to a few references. By the way, at the bottom of each slide, you will see a few references that you might be interested in exploring further later on, and I will be more than happy to share the slides with any of you so that you can dig more after this presentation. Well, if you look at commercial harvesters, typically they deliver in optimal conditions tens of nanowatts and maybe a few hundreds of nanowatts per square millimeter or cubic millimeter, and even down to nanowatts in unfavorable conditions. Now, let us assume that we have this power budget because we want to keep the harvester in the millimeter scale. So we want the system, the IoT systems to be, the system to be unobtrusive, so millimeter scale. Well, in that case, let's assume we have a very simple microcontroller unit, let's say an ARM Cortex M0, and let's say a typical configuration, 100 kilogates. Well, if you divide nanowatts or tens of nanowatts by 100 kilogates, this results into deep sub-picowatt per gate. Well, as you understand, the typical leakage, even in high VT flavors of low leakage technologies, this is at least several nanowatts, at least. This means that we need to actually reduce the power consumption compared to pure leakage by essentially 2 orders of magnitude. Well, this means, and that's very interesting, that's the first finding that you should really retain in this presentation. You actually need, if you want to comply with the power budget offered by practical harvesters, you need to run at a power that is even below leakage. That seems hard to do. Well, it's not easy, but it actually can be done, as I will show in the next few slides. So overall, we don't have really a single target for event-driven and most recent IoT devices, and certainly next-generation IoT devices. You actually have 3 targets. The first is minimum energy, so that the corresponding power, whenever you perform a certain operation regularly, will be minimized. Then you want to scale up to maximum performance, second target, whenever an event occurs. And in that case, you need much more performance than in the common case. And then third, we need to pursue minimum power whenever a power event is occurring, which means that the power from the energy harvester, assuming that the battery is now discharged, this is the power event I was referring to. Now you have to comply with the very tiny power budget of the harvester, which means you need to really reduce power as much as possible. So 3 targets, not 1. Well, the first one, minimum energy, has been explored in all possible ways in the last 15 years. And I will say very little about this. So basically, you want to optimize the voltage around the minimum energy point. which is well known to exist in any technology, and it depends on the specific architecture of the system. This has been explored extensively, so I will not say much. So voltage scaling certainly helps. And you also want to reduce the design margin of process voltage and temperature variations at design time. And here I'm just pointing out at a few publications we have published to mitigate and solve the problem, or to have even a margin, process voltage temperature margin elimination by measuring the actual minimum clock cycle through timing sensors. Let's move on, which is what lies ahead. So this has been done extensively. So how do you scale to maximum performance occasionally without compromising the minimum energy operation? So without compromising the first target? Well, before doing that, let me just observe that typically you're going to operate in any, let us start with simple with a digital circuit, and then we'll expand to sensor interfaces and power management. Well, typically transistors are going to operate in three wide ranges of voltages, which are strong inversion, about threshold operation, moderate inversion, which is near threshold operation, and weak inversion, sub-threshold operation. And if you look at a few designs that have been proposed over time, you can see that the performance degradation at the minimum energy point compared to the maximum performance, which means nominal voltage, is in the order of several tens of x, okay, and up to 2 orders of magnitude. Whereas the energy improvement at the minimum energy point compared to the nominal voltage tends to be an order of magnitude or sometimes lower, okay? So the performance degradation is heavier than the energy benefit that you get out of it. Now, the reason why actually it's not very easy to pursue at the same time maximum performance and minimum energy operation is twofold, actually. The first is, if you look at the clock path of a digital IP, it might be multiply and accumulate array or a microprocessor, is that the clock network actually is optimized at a given voltage in all practical designs and in all commercial designs, by the way. But actually, the number of clock repeaters heavily depend, the optimal one that will minimize the clock skew and will optimize the clock skew versus energy trade-off heavily depends on the voltage. So the question is, should I actually design optimally the clock network at nominal voltage so that I will have maximum performance, but then I will degrade energy efficiency and even reliability at lower voltage, or vice versa? So we have to make a choice traditionally. And same applies to the microarchitecture. So should I use a large logic depth or a lower logic depth? Because this actually changes completely the leakage versus dynamic energy trade-off. And this, in turn, translates into a different energy performance trade-off. And again, if you set this properties and you make these choices at design time, you're not going to be able to pursue at the same time maximum performance trade-offs, and target whenever performance is needed, or minimum energy trade-off or target whenever, in the common case. So at design time, if you don't have enough flexibility, you need to choose to privilege, to favor performance or energy. You can't have both at different times with the same circuit. So what is the solution? And on this, I'm really referring to a book that we have published a couple of months ago on adaptation for digital circuits. So you can dig more and have a look at this book to know more about this. Here, I will give you really an overview of the challenges that we have recently solved and the challenges that lie ahead. So overall, what you want to have is reconfiguration, both in the clock path and in the data path. This is what we are going to talk about in the next 10 minutes. Let's get started with clock networks, okay? And we want to introduce reconfiguration. In a traditional clock network, and I'm referring to the blue curve, if you are designing at nominal voltage, there's nothing you can do. This will certainly lead to a deep clock network, like the one on the top here on the right of the slide. You will have several levels of clock repeaters because you have to minimize the wire delay so that you can run at high speed. So you are going to interrupt the wire delay, the wires, as often as necessary to minimize the clock skew and maximize the performance. And if you reduce the voltage, you can see that the clock skew increases simply because at low voltage, so I'm referring to this end of the curve, at low voltage, actually, the wire delay remains the same. The clock repeater delay becomes much higher. So now you don't need to actually insert as many repeaters. So you will prefer to have what is called a shallow clock network. But the thing is that at design time, you have to choose whether to have a deep or a shallow clock network. So if you choose a shallow clock network, what happens is that here, you're going to have a low clock skew at low voltage, but then the clock skew at high voltages, so nominal voltage will be much higher. So it means that now the performance will be impacted very heavily, will be degraded. So what you can do is to go beyond traditional design frameworks and introduce the concept of reconfigurable clock networks. The only actual difference between a fixed conventional clock network and a reconfigurable clock network is the presence of this bypassable clock repeaters. So this can operate in two different modes. The first is, let's say, at nominal voltage, you want all of them to function as clock repeaters. So they are not bypassable. They are not bypassed. They operate in normal mode like any other conventional clock repeater. So you can pursue high speed. Instead, at low voltage, you want to eliminate most of them. You want to bypass most of them. And this is done by selecting the bypass mode in those clock repeaters, where you have basically a switch that bypasses and merges the neighboring wires to have longer wires and a different subdivision of the clock network between different levels. And this can be done, for example, this is just a possible implementation. This can be done in many other ways. This is the topology of a bypassable clock repeater. In normal mode, this is off, and this works like a normal repeater. In bypass mode, instead, this will be turned off through sleep transistors, and then you have a pass transistor that is just that connects the input and the output. Well, that means that this no longer operates as a logic gate. It operates like a short circuit, basically. The good thing about this simple approach is that you will actually need to bypass clock repeaters only at very low voltage, right? And this means that if you just apply nominal voltage, which is invariably available in any design, to the gate of these transistors, these pass transistors actually will be inherently much stronger than all other transistors. So it means that you can actually keep them pretty small. You don't need to upsize them significantly. And this explains why in, for example, in a 256-point FFT design that we have demonstrated, and then we'll talk about that in the next few slides, the area overhead of this approach is very limited, and it's less than 2%. So how to make this work? Essentially, you want, based on the voltage, you want to have a certain number of bypassed repeaters. No bypass at the highest clock frequency, all bypassed at the lowest frequency, right? And anything in between for intermediate voltages. Okay, so apart from the traditional table that associates voltage and frequency for dynamic voltage frequency scaling, you need to augment this table with the indication of which clock repeaters need to be bypassed and which should not. Okay, so from an implementation point of view, actually it's pretty easy to have reconfigurable clock networks. You just need to augment the traditional DVFS table with the third column that specifies what the configuration of the clock repeaters should be at every voltage. Now, once you optimize, you choose the optimal clock skew optimal configuration of the clock repeaters, you're going to have these blue curves in terms of clock skew versus voltage. As you can see, the clock skew in terms of FO4 delays, where FO4 is the well-known delay of a single inverter gate driving 4 equal inverters, remains a very small fraction of FO4, as it should be. Okay, so you don't see the explosion of the skew at low voltages. And to be more precise, if you actually adopt a fixed clock network, this is what you get. At low voltages, you get an increase in the clock skew by more than 3 times. And this is very harmful in terms of both reliability, robustness, because now hold time violations in registers is much more likely, as well as performance, because now the fraction of the clock cycle eaten by the clock skew is increasing, which means that now the performance is degraded. Instead, if you adopt the optimal configuration, you're going to reduce the skew and you are going to keep it basically nearly constant or so. Okay, you're going to mitigate this very substantially. What is the effect of this? Well, let me just comment on the 2 aspects that I mentioned before. One is hold time violations. Well, if we actually manage to reduce hold time violations, thanks to reconfiguration, what happens? Now you can actually operate at lower voltage because the clock skew is reduced. And that's exactly what happens. You can reduce the operating voltage, the minimum operating voltage, by more than 100 millivolts. Now your sensor node can actually have wider voltage scaling. And it's and this also improves the yield because the hold margin is increased. At the same time, of course, you get an increase in performance, as you can see here, 8%. That's not very significant because when you operate at, let's say, 0.4 volts, a minimal increase in supply voltage will actually get you 8% of performance increase. So that's not really a real advantage. What is an advantage is that now you can actually reduce the operating voltage. It means that you can benefit from the farther quadratic energy benefit offered by voltage scaling. And that's why you're going to get an 1.4x, so 40% energy reduction compared to the original fixed design. Okay? And this explains why clock network reconfiguration allows to improve the trade-off between performance, reliability, and energy. It basically relaxes this trade-off. It allows to improve all of them whenever you're pursuing higher performance, lower energy, and higher yield and higher reliability. Now let us look at the data path. We have talked about the clock path. Let us talk about the data path. Well, essentially, the question is, should you adopt a higher logic depth, so few registers with very long pipe stages with a lot of cascaded logic gates, combinational logic gates, or you want to go the opposite, so a lot of registers with very little combinational logic between neighboring registers? Well, as usual, there is an optimal logic depth. that determines the minimum energy point. And this minimum energy point actually depends on the architecture. And by the way, you might want to actually adapt this minimum energy point depending on the performance level that you're pursuing. Let me be more specific. And let us consider the case where you just set VDD. Okay, you set VDD and you want to choose logic depth. As it's easy to imagine, shallow pipelines, it means few registers and long combinational logic paths are preferable because you have fewer registers, right? So at a given voltage, the deep pipelines with more registers have higher energy, right? At low voltage, it's the opposite, because deep pipeline has actually lower energy simply because you have shorter pipeline stages, so shorter delays in the combinational logic, which means that you integrate leakage, so the leakage per cycle becomes smaller because the clock cycle is smaller, right? So again, if you choose the logic depth at design time, you have to choose whether you have high energy efficiency at higher voltages or lower voltages. Instead, if you have adaptation, you can adapt to both and get the best energy efficiency in both cases. And if you look at the comparison of different microarchitectures at the same throughput, then similar configurations considerations hold. They are actually inverted, but you basically come out with the same conclusion. If you choose a design time in a fixed, rigid manner, you're not going to be able to pursue energy efficiency at all voltages. You will achieve it in certain ranges and not others. So the question is, how do you reconfigure microarchitectures? The answer is pretty easy, and you can look at a paper that we published 2 years ago in JSSE. Essentially, you have bypassable registers. Normally, you don't bypass, so you have a multiplexer at the output where you don't multiplex the flip-flop. So basically, the flip-flop keeps operating like a normal flip-flop. Instead, if you want to bypass it, you're going to select the other input of the multiplexer so that the input of the flip-flop goes directly to the output. So basically, the clock is irrelevant. You're not really latching the information, okay? And then if you bypass, you're essentially merging. If you bypass this, you're going to merge this into a single pipeline stage, right? So you're now virtually expanding the logic depth of this pipe stage. Now, how do you choose this, and how do you actually enhance traditional voltage scaling, voltage frequency scaling with the ability to merge pipe stages and adaptively change the logic depth of pipe stages? Well, the answer is the same as before. Apart from the traditional table with voltage and frequency, you add the configuration of the registers, choosing whether you need to bypass or not. And you will choose the configuration that maximizes the energy efficiency, okay, based on the criteria that we mentioned before. So again, the implementation is actually quite easy. You just need to enhance the DVFS table with this third column. And if you want to do all of them, so data path and clock path being reconfigurable, you will have a third column with clock reconfiguration and a fourth column, which is data path reconfiguration. Let me just share with you what happens with an example, which is pretty representative of practical applications. You have 256.16-bit radix 4 fixed point complex FFT, which has hundreds of kilogates. So that's representative of typical design IPs for IoT, not very big, not very small. And what you can see is that you can have, at about threshold voltages, you can reduce the energy by 25%. So this is what we are referring to. At lower voltages, you can do pretty much the same. You can reduce energy by 30%. So what we are seeing is that the optimal selection of the microarchitecture, so the data path configuration, allows you to reduce energy both at higher voltages and lower voltages, depending on whether you want to have more performance or lower energy and power in the common case. So you don't need to choose at design time. At runtime, depending on what performance trade-off you're pursuing or what performance target you're pursuing, you can adapt and reduce the energy in either case. And the throughput is degraded by the presence of multiplexers and reconfigurable registers by less than 6% at the maximum maximum performance target, with the area increased by 3%, which is quite okay with for all practical purposes. I will skip this and I will focus on design methodologies. This is actually a talk by itself, so I will probably skip through. But I would like to mention that we have also developed a complete design methodology and a design flow for reconfigurable microarchitectures and logic depth, as I mentioned before. And this can be applied to any practical design. It's available on GitHub. You can just download it and use it. So you can just use this QR code and download the set of scripts that we have created to enable this capability in design and architecture agnostic fashion. Let me just share with you that the materials that we have put on GitHub allow to first do a pre-designed path analysis to foresee what the benefits will be after the design, but you can actually foresee this before doing the actual design. And second, these scripts and the overall design flow actually operates on gate level netlists. So this means that even if you have, let's say, an ARM core or any third-party design IP that is being synthesized and it's obfuscated because it's protected, because it's third-party, you can still adopt this methodology without any limitation. So you can apply our methodology to your designs or third-party designs. And you can refer to these two publications if you want to know more about these design flows. One is TVLSI, a paper that we published a couple of months ago, and one is the book that I mentioned at the beginning of this presentation. Now, this only solves two of the three design targets. There's a third one, which is minimum power operation whenever the battery is no longer available because it's depleted. And this is actually a very realistic scenario and very frequent scenario whenever you miniaturize the system to millimeter scale batteries. Such small batteries will get depleted very often. And in that case, you need to survive and keep sensing and processing even when you have only power from the energy harvester. How to do this? Well, to follow through the thread that we have gone through so far, I will start from MCUs, so digital subsystems, and then I will enrich with power management and sensor interfaces. Well, basically what you want to do is to extend the power dynamic range offered by voltage scaling. You can actually extend it down to nanowatts as required by energy harvesters by using other logic styles, for example, dynamic leakage suppression logic style proposed by University of Michigan, as well as Q11 a few years ago. But this doesn't allow you to actually have a complete and flexible trade-off. So what you want to have is to bridge the gap between the existing standard CMOS logic style and other more sophisticated logic styles that reduce power. So you really want to fill this gap and have a continuous power performance trade-off. This can be done by using an approach that really achieves both the properties of CMOS logic whenever minimum energy or higher performance is needed. So this is standard CMOS logic. And you want to also reconfigure your system and your circuit to mimic DLS, dynamic leakage suppression logic that I mentioned in the previous slide, whenever minimum power is being pursued. How to do that? Well, as you understand, architectural reconfiguration is not enough. You really need to go down to the circuit level. So you need to introduce what we call dual mode logic, which is at the right of this slide. And I will talk about this in the next 2 minutes. You can find more details in a paper that we published at ISSCC 2 years ago and other journals that came after. So the main principle of dual mode logic is that if you actually turn on these two transistors, 1 and 2, in each standard cell by just raising the gate voltage of this NMOS transistor, the upper transistor, beyond VDD, and the PMOS transistor below ground, and this can be done with very low power charge pumps, very low power, because they are just driving a capacitive load. There is no DC current being absorbed by these transistors, right? So in this case, this will go to VDD and this will go to ground. Well, then this transistor, these two transistors are just an inverter gate. So this resembles conventional CMOS logic. Okay, so this circuit is able to mimic standard CMOS logic. At the same time, if you instead turn off these two transistors in green, now the rest of the circuit in the standard cell mimics, is actually completely equivalent to DLS logic, which is femtowatt per gate type of power, deep subleakage as needed. So you have reconfiguration based on whether you turn on those two transistors or you turn them off. And this is what you get. Dual mode logic is able to, on one hand, achieve minimum power that is almost best in class compared to others. This is nanowatt level, even sub-nanowatt level for practical MCUs. But at the same time, they can achieve a performance that is comparable to most or superior to most existing MCUs. So this is MCU, 16-bit. This is MSP430, like MCU. And as you can see, it has the ability to go down to nanowatt, while still, so it means that it's suitable for continued operation based on millimeter scale harvesters, and it has 6 orders of magnitude power performance trade-off. And by the way, this tells you really what each of those techniques enables. So voltage scaling allows 2 to 3 orders of magnitude power performance scaling. Then if you apply data path or microarchitectural reconfiguration, you go up. You extend the dynamic range by another order of magnitude. So this one. Then if you want to extend by another 2 orders of magnitude, you really need to go for dual mode logic. And that's quite expectable. Basically, in the first category, this one, voltage scaling enables power performance scaling. Then if you want to further enhance it, you're going to go for architectural scaling. And then if you want to further enhance it, you want to go for circuit reconfiguration, right? And you reach 6 order of magnitude scaling. Now, let me clarify that this is just an example, and this can be applied immediately to sensor interfaces. And this is just an example. So the main challenge whenever you have a complete system where you have power management, sensor interfaces, as well as digital subsystem, what you want to do is to remove the power floor, which means the minimum power of any existing subsystems, so that all of them will keep scaling if you need to, at the cost of lower performance, of course, but you don't want to have a power floor imposed by any of those, let's say, leakage for digital or bias currents for analog. You actually want all of them to keep scaling down if you need, and if the battery runs out of energy. And this has been done in our group and has been demonstrated in the last 2 years. And we have shown that sensor interfaces, especially mostly digital sensor interfaces, instead of being just digital assisted, you really want to move to mostly digital so that you can get the similar benefits as the digital subsystem. And both of them, both the analog and the digital subsystem, are able to scale down in terms of both power and frequency in a coordinated manner. So if you scale down the power on one of these two, the other one will adapt equally. And same in terms of performance. So none of those will be the performance or power bottleneck. They will scale together. And this is an example. I will not go through the details, but I will encourage you to go through the JSSC publication of a few months ago. Basically, we presented a multi-sensor interface that is able to coordinately scale with a microcontroller unit and go down to nanowatts and up to a few mega sample per second sample frequency. Well, this tells you that for IoT, whenever you have power, you can actually cover most of the applications. So you can go up to mega sample per second. But if you don't have power because the energy in the battery is really running out and you need to comply with the power budget of an energy harvester, then you can run down to 3.1 nanowatts, all included. This includes digital power management as well as sensor interface. So again, you have 5 to 6 orders of magnitude power performance trade-off, including sensor interfaces. How useful is this? Because this is, of course, more aggressive than architectural reconfiguration. Well, this actually enables an unprecedented scaling in terms of power and compliance with the power budgets coming from harvesters, even under very unfavorable conditions. Let's say you are operating with a 4x4 commercial harvester, solar cell. So in indoor light, this is what you're going to get, okay? You can go down to this, and this is what voltage scaling allows you to do. If you want to keep operating under indoor light, and this is the typical indoor light, our approach allows to do that. So even with no battery, the system keeps going. Now, let's assume you're operating in a home environment with very dark light in an overcast day. So we're talking about tens of luxes, okay? The system keeps operating because the power is still in the order of hundreds of nanowatts from the harvester. Now, let's assume it's going pretty dark, 10 lux, okay? And now let's be even more extreme. Let us go to 1 lux. Well, you know what 1 lux is? 1 lux is moonlight. So yes, and if you actually look into this QR code, this will lead you to a demo, live demo, that you can actually watch with your smartphone. Essentially, the system is able to run down to moonlight. It means that it's unstoppable. It can be always on, even if there is no energy in the battery, and even if the harvester conditions are very unfavorable. So on all practical respects and under any practical lighting condition, our system proves to be always, truly always on. And there is a lot of work going on to further reduce this the power cost of the different subsystems. So here you will find a summary of publications that we have in this area. And I would like to summarize beyond this. So we have covered amplifiers and ADCs and DACs and voltage references, oscillators, and so on and so forth. So all practical peripherals that you find in an IoT system. But beyond that, I would like to summarize and give you the, the fundamental message of this presentation. Next generation IoT systems are not going to be single target. They actually are going to be multi-target and event-driven. Why? Because first, you want them to be minimum energy per operation whenever they are operating under battery energy. Whenever there is no energy in the battery, or actually, sorry, before that, whenever there is an event of interest, signal event, you want to respond and increase the performance to perform data analytics on chip. So this means maximum performance. So you need to scale up performance. How to do that? Architecturally and through conventional voltage scaling together. This buys you another order of magnitude of power performance trade-off. Then, if the battery is running out of energy, you want to keep running, and this means that whenever there is a power outage, a power event, you want the system to keep sensing, processing, and storing into the memory at nanowatt level, so minimum power operation. And then a fourth capability that will be required is, let's say there is really no harvesting power at all, or so even lower than moonlight, so something that is really catastrophic. You still want to retain at least the basic events that were being stored in the memory. In that case, you want to at least keep the system functioning correctly and retaining the basic functions and the basic information stored, even if there is really not much power from the harvester. And then let's wrap up. I guess we all remember what this is. Probably keeps us in a good mood. Let us wrap up. Let us see what we should retain from this talk. First, next generation IoT devices are not going to be single target. They are going to be 3 targets. Minimum energy, to have low power in the common case when they are battery powered and always on. Second, maximum performance, so you want to boost up the performance by at least an order of magnitude whenever, or even more, whenever you need to perform data analytics of events of interest. And then if there is a power event, so no battery, you want to respond by reducing the power to the level that is available from the harvester. And this requires a very wide and uncommonly wide power performance trade-off. And this is accomplished through traditional voltage scaling. It only gives you so much, right? Then you have to augment this through architectural reconfiguration, and you buy another order of magnitude. And then you can have circuit reconfiguration, which buys you from another 1 to other 2 orders of magnitude. Well, these capabilities, other than keeping our systems on and mostly available all or most of the time, allow us to shrink batteries by 1 or 2 orders of magnitude, which actually is a good thing to do, not only because of the cost and the implications in terms of form factor. So shrinking batteries or eliminating batteries is a good thing to do on those respects, so form factor and cost. But eventually, considering that we are going to deploy otherwise 1 trillion batteries in this planet, and this is going to create an unprecedented level of pollution, well, the removal of batteries, or at least shrinking batteries by 1 to 2 orders of magnitude, will make our planet a little greener, which I think is a mission that we really need to think about when we do research. Our planet cannot really take another extra 1 trillion batteries. Well, before I say, I will leave the floor for questions, I would like to really thank my group and my students and researchers. It's just it would be just impossible to do what we are doing without their contribution. So what I do is I share with you what we are doing, but the real work is really being done by our students at the Green IC group in Singapore. And then, if you're interested in digging more in scientific contributions that provide some new directions. You can look into a few special issues that we have been leading. This is TCASS-1 and JetCASS 2 years ago. One book that actually, this is the one that I presented at the beginning of this talk. This is a Springer book on adaptation of digital circuits, and another book on IoT. This is actually the first book on IC design for IoT that was presented a little more than 2 years ago. And an upcoming book, if you're interested in how to get rid of 1 trillion batteries and make our planet a little greener, well, that's coming up in a couple of months. But I cannot really tell you the title, so it's all top secret right now. So just stay tuned. And if you're interested in attending our mid courses, this is the first actually in Asia on energy constrained integrated systems. Just stay tuned and feel free to contact me if you want to have more information. We had the first edition, and during the COVID year, we didn't have it, and we're going to have the 2021 edition in a couple of months. So thank you very much for your attention. I will be more than happy to answer your questions. Thank you.
Okay, thank you, Massimo, for this very interesting talk. We have many questions here coming in the channel from the audience. The first one has to do with asynchronous, okay? Marco Sartori, a PhD student here in Porto Alegre, and also David Harvey from Liverpool are asking those two questions regarding the clocking strategy. Why not get rid of the clock networks altogether? I understand going asynchronous. And from Liverpool, why not go for asynchronous clocks? No clock delay is an issue, only edges and level changes. So there are questions related to timing disciplines that they are considering as alternative for ultra low energy.
Well, first of all, I would like to thank for the very good question. And conceptually, both attendees are totally right. Conceptually, it would make sense to get rid of clocks. In practice, this would be feasible only if they can prove that there is full support from CAD tools, commercial tools, or design methodology that allows to deal with timing in an automated manner. And that has proved to be a challenge. So in practice, this is very difficult to do, and that's why you don't find much application in the commercial space. So it's not impossible, but it needs to be done. So those ideas are relevant and useful as long as design methodologies dealing with timing are available or are made available. And I guess this answers the question. It's a two-sided answer, depending on which side you want to look at.
Okay, I have a question myself about the bypass clock network paper. To let's say minimize the delay uncertainty in the clock network and the insertion delay, you go full drive overdrive in the bypass transistors, which bypasses the buffers. So my question is, what is the implication of using still the high voltage overdrive at the bypass in terms of the power manager requirement that is needed? Also in the logic that you proposed later on, you need to do a full drive at the head and tail transistor. So what's the implication for the power manager itself having still to require to go up to boost the voltage to nominal value, let's say?
Okay, well, I would say that this really depends on the system that you have. If you have battery, you already have your voltage available. You're going to have the nominal voltage for sure. So I guess that your question is related to those design scenarios where you don't really have a battery.
Right. You have batteries are different, yeah.
Yeah. So you have to boost up the voltage. Well, but in practical cases, certain subsystems still need a much higher voltage. This might be always on. This could be, let's say, analog subsystem. Many times it needs to be near, it cannot be near a threshold. It can be, 0.8 volt. And in that case, you can still leverage the availability of much higher voltage to increase the strength of the pass transistors to reduce their resistance, or conversely, to reduce their size for a given allowed resistance. So even if you don't have a battery, you still need voltage domains with quite higher voltage. That is not 0.3, right? And in that case, you can still use it. And the good news is that the load that is offered by these pass transistors is purely capacitive. You charge them once and you're done. You don't need to provide any further energy.
Okay, thanks, Massimo. On slide 34, okay, you were mentioning the area overhead that you had from the methodology on slide 34. What is the chip function, chip module that you use for calculating this area overhead, in which are providing the microarchitecture reconfiguration for the pipeline stages and bypassing timing walls?
Okay. Well, first of all, this is an example based on an FFT. And the reason why we chose FFT is actually because it's not very easy to pipeline, right? So you have actually a quite diverse set of paths. You have LUT paths, you have combinational paths that tend to be signal processing like. So you have basically multipliers, adders. You have FIFOs. So we wanted to show that actually the methodology and the benefits are obtained even in architectures that are quite diverse. The second thing that I would like to highlight is that although I didn't present this here, we actually proved this year in a JSSC paper that you can look up through in our website. We have done the same on a microprocessor. And actually, repipelining a microprocessor might seem to be very difficult to do. And we proved that that is not true. So if you just repipeline a processor in a conventional manner, you're going to deal with all the hazards that come from the repipelining of the processor itself. Well, actually, there are ways to repipeline processors without touching at all the control flow. One way to do it, which is what we have explored, is to have time interleaving. You basically, this is very easy to do with the methodology that we have come up with. You double the registers, you make them bypassable, then you redistribute, you retime so that they will make the pipe stages balanced. This means that if you bypass the added registers, the processor will run as it was. It's single core operation. If you instead enable, you don't bypass the additional registers, these registers will basically perform computations like a second core. It's essentially the concept of multi-threading, but implemented in a way that is much simpler than usual, okay? And multi-threading, by definition, and time interleaving, by definition, allows the computation to be completely segregated in two different threads. Even cycles, you're going to do processing for thread 1, odd cycles for thread 2, and they will never interfere. So you don't need to change at all the control flow, which means also the whole software stack. You can use this very same compiler and applications. So basically, you get 2 cores instead of 1 at the cost of area overhead due to the additional registers, which is percentage points in typical microcontroller units. Of course, these approaches are unconceivable in very high-performance microprocessors like for servers. That doesn't work, right? But as long as you have a logic depth that is not very aggressive, and all IoT processors are like that, then you can actually do that, and you can basically double the throughput at percentage point type of area overhead. And I guess this answers your question.
Okay. Well, the question also was answered in terms of the area overhead in the slide 34. It's calculated for this function that you are showing here.
Yes.
Good.
Correct.
You showed a very interesting result on, let's say, scaling the analog modules, bias current for the analog modules, and concurrently with the digital function. So my question is on slide 45, where those results are let's say, summarized. My question is, what are the sensor analog modules that you were scaling, the bias current and so on and so forth? That's exactly in this slide 45. Slide 45. So
Yeah.
you are scaling the analog. Which are the analog sensor modules that were scaled in this coordinated speed scaling?
Okay, we are actually keeping all of them on, all of them. And the speed, so in terms of power, this is the worst case power. It means that it's accounting for all sensor interfaces being turned on simultaneously. So we are talking about capacitive. So we had basically an external capacitor for proximity sensing, light sensor, as well as an ADC. An ADC to connect an off-chip sensor. So all of this is running. And I can tell you that the speed limiter is the ADC. And this is running down to hertz at low, the minimum power. But if you have power to spend, you can go up to 2.4 megasamples per second, which is, I believe, quite respectable and definitely covers most of the IoT applications.
Okay, so the analog function is less amenable to downscaling because the ADC will start not functioning correctly at very low voltage.
No, it does. So these results, the ADC is we introduced a new ADC architecture.
That it's a full custom. It's not off the shelf. Okay.
Yeah.
Okay. It's a flash one with a full custom. Okay. Good.
Yeah. So basically, in 10 seconds, you can imagine that any capacitive type of ADC doesn't work, because if you want to slow down to hertz whenever you don't have any power, but you want to still keep sensing, as you understand, capacitors don't get along with leakage. So if you slow down operation, those ADCs are not suitable. Instead, flash ADCs, at least up to a certain resolution, and then we actually are working on hybrid ADCs to increase this resolution. You can think of hierarchical flash, right? Where you can lower down the voltage down to 0.3. So all these results are obtained at 0.3 and down to 3.1 nanowatts, powered by a solar cell, no battery whatsoever. Okay,
that's great. Mm-hmm. Well, that's great. We have one last question because we are running over time already. That's the last question. People out there in the YouTube channel watching the streaming. Juan Pablo from the Saytech company here is a designer. He makes the following comment: we know that some minimum energy designs are sometimes impractical due to the local timing variations in CMOS process. Do you work or propose some ways to mitigate those process variations when you are operating at near threshold, let's say 300 millivolts or so? So okay. His question has to do with mitigation of the extreme increase in variability, timing variability, which has to, by the way, be accommodated with when you reconfigure the data paths in the pipelines.
Yeah. So first, let me tell you that typically the type of architectures that are suitable for extremely low voltages tend to have reasonably long logic depth, and architectural reconfiguration can help you do that, right? So at higher voltages, you might actually decide to take advantage of the speed, but at lower voltages, you always have the
Well, it looked like we had an interruption. We are having some problems. We are having problems with audio from the speaker in Singapore. Well, that was the last question.
Sergio, are we connected again?
Dear Massimo, we are back. We are back streaming again. We had an interruption on your reply and your answer when you were talking about, let's say, the how to cope with variations, timing variations at near threshold.
Okay, so at ultra low voltages, because of the you can always leverage microarchitectural reconfiguration to increase the logic depth at very low voltages, because this will greatly average out the effect of process variations, right? And by the way, at ISO throughput, this also actually minimizes the energy. The other consideration that I would like to make is this. The effect of variations at very low voltages is largely dependent on the type of technology that you're using. I can tell you that whatever we have shown, we have measured at least 15 to 20 dyes to characterize process variations. And in the papers, we will find voltage and temperature variations. We are using here 180 nanometer technologies for a simple reason. If you want to go well below, the microwatt wall, you want to go down to nanowatts, there is no way you can use, a 28 nanometer technology. You need to use lower leakage technologies and low cost. So, right. Of course, you cannot have everything. Getting down to nanowatts costs something. You're not going to be able to run at gigahertz for sure, and you're not going to have very large scale systems. So all comes at a price. Now, having said that, the heterogeneous integration is actually what can enable the best of the two worlds, and we haven't explored, at least in publications yet, but that's a very interesting area to explore, which is, on one hand, you want to have always-on systems or subsystems that still process and sense, even if there is no battery and there is very little power from the harvester. Whenever you have more energy, then if you want to have more sophisticated digital processing with higher density and at higher power, then you can mix and match, and you can have chiplets of, let's say, 180 always on, and then occasionally on 40 or 28 nanometer or 22 nanometer, right? So that's a space that is largely unexplored, and I would encourage all of you actually to explore it. There's plenty of opportunities there, and we are
okay. Very good, Massimo. Very good. Well, thanks very much, Massimo, on behalf of CAS Society and the local chapter here. Thank you very much for presenting such an interesting, talk. We're looking forward to your next book. Excellent work, and we'll be seeing each other soon, hopefully here in Brazil. Bye-bye.
Yeah, see you all.